Alright, today we're going to talk about some non-uniform circular motion, and for the most part these notes can be done on your own, but I wanted to give you guys a couple of hints regarding a few of the things. So I would suggest you pause the video right here and read at least through this first page on your own, because I'm not going to read it to you, there's no need for that, and you do want to kind of understand where we're going. Okay, hopefully you read through a couple things, and if you didn't draw your delta V yet, this is how we were going to do this. So remember that a change in velocity is equal to the final velocity minus the initial velocity. This vector right here is the final velocity, and this vector right here is the initial velocity. So if I want to do some vector addition here, I would go ahead and draw this first vector, the final velocity. And it's harder to do that in the app I use for the video, but you can do a better job of it on Notability. And then we want to draw the negative of the initial velocity. So that's going to look something like this. And notice that the initial velocity is slower, so that's why I drew that line much shorter. Then we can see that our change in velocity is going to be this right here. There's my change in velocity. Now it's really important to notice that this vector is no longer pointing to the center of the circle. So that's why we end up with an acceleration that's not just centripetal towards the center, but also a tangential acceleration as well. So when we look at this next page then, we still have our original initial velocity and our final velocity. Here is our vector for acceleration or change in velocity, but acceleration is just change in velocity divided by time. And you can see that we've split this up into two components, a centripetal component and then a tangential component right here. This second diagram is still showing the same acceleration vector without the velocity vectors, just to make it more clear. And again, we still have a tangential component right here that's tangent to the circle that's going to cause the object to get faster. And then we have our centripetal component of the acceleration, which is going to cause the object to continue to move in that circle. And you can see here that with that information, we can always determine the centripetal acceleration the same way we always have, using our v squared over r. And then our tangential acceleration is going to be the same way we always have as well. We're going to use our F net equals ma, and the net force that's tangential to the circle at the point will be the force components that contribute to that net force. Or if we know something about the speed, we can always determine the acceleration, the tangential acceleration, by taking the change in speed divided by the time. So what I want to do in the next slide is look at a quick example of how we do that, and then you can try some problems as well. So here we've got a car driving on a flat road, and the road is curved, and the curve has a radius of 200 meters, and we know that the car is going to increase its velocity. We start out with a velocity of 20 meters per second, and my pen's not writing very well, there we go. And we end up over here with a velocity of 30 meters per second, and the time it takes for that to happen is 2 seconds. So the first question asks at part A, the car's tangential, we need to calculate the car's tangential acceleration during that time. So tangential acceleration is just a change in velocity divided by time. And we're only looking at the magnitude there, so really I could write it that way. And I can see that the change in the magnitude of velocity, 30 minus 20, is just 10 meters per second. Divided by 2 seconds, I get that the tangential acceleration is 5 meters per second squared. Nothing too interesting there. Part B says, okay, calculate the centripetal acceleration. Well, our centripetal acceleration is still v squared over r. So we can see that at 20 meters per second, our velocity is 20 meters per second squared, divided by our r is 200 meters. So let's see, what do we get? 20 squared is 400 meters squared per second squared, divided by 200 meters. We get 2 meters per second squared for our tangential acceleration. Now that's at exactly 20 meters per second. Later on, our centripetal acceleration, v squared over r still, is going to be 30 meters per second squared divided by 200. So what does we get? 900 meters per second squared divided by 200 meters you can go ahead and do that math on your own. You can check it with the key at the end as well. So when they ask what is the magnitude and direction of the car's acceleration at 20 meters per second, draw this vector on the diagram above and label the angle. So let's take a look. We know that we're going to have I'm going to change the color of the pen here just so we can see it a little bit better. We know we're going to have this centripetal acceleration, and we calculated that to be 2 meters per second squared. And we know we're going to have this tangential acceleration that we calculated to be 5 meters per second squared. Now, drawing it the way I did is not super useful if we're going to do some vector addition. So I am going to erase this right here because I want to draw this a different way and show that really that 5 meters per second squared could go right there. And then we can see that the resultant there would be my magnitude of acceleration. So I could go ahead and figure out that magnitude is just the square root of 5 meters per second squared, all squared, plus 2 meters per second squared, all squared. I have to take the square root of that, so I'll let you do that math. And then the angle that occurs at, theta, would be the inverse tangent of, let's see, 5 over 2. And again, I'll let you do that math and check it in the key. The rest of these problems are practice problems for you to work on, and there is a key at the end. This first one's a little tough because it's something we haven't really experienced before, so I want to give you a little bit of a hint and just tell you that what we've got here is just a pendulum, and we're holding a mass for the pendulum up not quite at level to the floor, but close. And then we are releasing it and letting the pendulum swing all the way back to the other side. So you can see that at point A, the velocity of the pendulum is 0 the instant we let it go. And then at point E, the velocity has again gotten to 0. So think about that when you are determining your centripetal acceleration and thinking about the centripetal acceleration. Because remember, our centripetal acceleration is v squared over r. So obviously, if we have a very small velocity that's getting bigger as we get closer and closer to the bottom, we're going to have a centripetal acceleration that's getting larger. And then for the tangential acceleration, thinking about that, think about how the net force is going to look. So we've only got two forces here. We've got this force that's going along the length of the string, and look at this vector here with our acceleration. That's mostly in the tangential direction. By the time we get to C, there is no tangential acceleration. So think about that as you're going through this problem and working on that problem. Then for the rest of these problems, really it's going to be key to draw a free body diagram and think about what's happening here. We know for this car right here, we're going to have a normal force, certainly. We're going to have a force of gravity. Think about which one has to be bigger. The common mistake here is to put static friction somewhere on the car as well, or even worse, kinetic friction. But we're going to model this right just like we looked at the pendulum on the previous page, that right here there's only a normal force up and a force of gravity down. We're assuming this car is going at a constant speed here, so we're not going to worry about the acceleration, the tangential acceleration. We're only looking at the centripetal. Other than that, good luck with the rest of the problems, and please feel free to ask questions when you get back to class.